Okay, this is lesson 4.3, and today we're going to look at two ideas, the absolute extrema and the mean value theorem. Okay? Now when I talk about extrema, I'm really talking about max or min. So here are some informal definitions of max or min. So when you're looking at a graph, you can probably say for sure, oh yeah, this is the max or the min by looking at where it's the highest and lowest point, right? But maybe you're thinking, if I said maximum, what do I mean? I mean, I see a whole bunch of maximums here, right? Maximum, maximum, maximum. So which one am I talking about? Well, that's why we have to use these words. Absolute, to represent the highest of them all, or the global maximum. This is where the y value is greater than or equal to all the other y values in the function. And similarly, if I use the absolute minimum, then it's the one that is less than or equal to all the other y values. So that would be this one right here. Yay! I should erase these ones here. Oops, didn't want to erase the whole graph. Well, let me just quickly use a different color. What about these other maximums here then, right? What about these ones? How do we describe those? Well, we call them relative maximums or local maximums because the y value is greater than or equal to all the other nearby y values. So it's the highest in that local region. That's what we call the local relative. And similarly, the relative minimum or local minimum is the same. It's the lowest in that particular region. Okay? When I use the word extrema or extrema, that just means give me the extreme values, the maximum values or the minimum values. Okay? And there's one more term we need to know. It's called critical numbers. And these are the x values at which the function exists, but the derivative is either 0 or undefined. And if you notice that all of these points where there's a max or a min, it looks like the slope is equal to 0. Or in other cases, if I even drew something like this, see this? Ooh, this is a minimum, but the slope's not 0 here. No, the slope is, that's right, undefined. Okay? So keep that term in play, critical numbers. The x values where the function exists, but its derivative is either 0 or undefined. Okay? And all this stuff gives rise to what we call the extreme value theorem, EVT. If the function is continuous on an interval from a to b, then we know that f has both an absolute minimum and an absolute maximum on that interval. Okay? That's what the extreme value theorem says. Continuous, must have an absolute max, must have an absolute min. Okay? And in practice, the standard method of finding these maximum values is by using what we call the candidate test. And the candidate test says this. If you want to find all the global max, guess what? You got to find all the critical numbers first. What are the critical numbers once again? That's where the derivative equals to 0 or the derivative does not exist. Okay? And then once you found those critical numbers, they're the x values, you have to actually find the y values at each of those critical numbers. And then also double check, and this is the part that people forget, the endpoints of the interval. Because quite possibly, like in our example up top here, the highest point is not one of the places where it's equal to 0, but at the endpoint. Okay? The endpoints. And then once again, once you've done all that, just compare and choose the least and the greatest. And there you have your absolute max and your absolute min. Okay? So note that absolute extrema can occur either at critical numbers or endpoints. However, relative extrema, the local stuff, can only occur at critical numbers. Okay? We don't consider the endpoint extrema to be relative, although some textbooks really do allow that, but really it's not. Okay? So knowing all these definitions, and you can go back and review them yourself, I'd like to see if you can quickly try questions 1 through 6 first. Okay? So pause the video now, try them, and then come back and unpause and double check your answers. Okay. Oh, excuse me. I'm tired. What is the absolute maximum? Once again, this is the y value, so the absolute max, I hope you said, is 4. Boom, right there. At what x value does that occur? Then, of course, it's when x equals to negative 4. So if I ask you what's the absolute maximum point, you would tell me that the coordinates is negative 4, comma 4. Good. What is the absolute minimum? If you said right here, and you wrote down negative 2, I'd say, because this is an open dot. So really, it's something really close to negative 2. How close to negative 2 is it? Is it negative 1.9? Negative 1.99? 1.99? How close is it? Well, we really don't know how close it is. And therefore, we really can't say there's an absolute minimum, because we don't say it's actually negative 2, and it's not negative 1.999 repeating, so because of that open dot, unfortunately, there is none. Okay. If I did fill it in with a solid dot, you're right, the answer would be negative 2. Okay. Now, at what x value does f have a relative minimum? So relative minimum means in the local region. And if you said x equals to negative 3, I like it. If you said 1, I like it. And also if you said 2, you're like, what? 2? Yeah, because that is the minimum value in the local region. That also works. And finally, number 6, at what x value does have a relative maximum? Well, if you just said negative 1, I'd be happy. And that's the only one. Good. So this is visually with a graph. But now how about analytically with a function? So I'm going to ask you, please find the global extrema of this function. And remember, the idea is the candidate test. What do we need to do first? Find out the critical numbers. How do we find the critical numbers? We set the derivative equal to 0. So let's find the derivative first. 1/3 times 3 is 1, so that's x squared minus 4x. If we set it equal to 0, notice we can factor on x, and I have two answers. X equals to 0, and also x equals to 4. Cool. Is there a place where f prime of x also does not exist? No, because this is a polynomial, so don't have to worry about that. Okay? Now, once you found your critical numbers, then you have to, that's right, calculate the y values. So really you should be finding f of 0 and f of 4. And don't forget the endpoints, so you should also be looking at f of negative 1 and f of 3. Now you're like, whoa, 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 whoa. I have f of 4 here. That's not in my interval. So guess what? Don't test it. It's not in an interval. Don't worry about it. Save some work. So we only need to choose these three x values, negative 1, 0, and 3. So let's go ahead and plug it in. Now, I'm asking you for the global extrema. Extrema is always the y value. So you're plugging it back into the, that's right, the original equation. And if you did that, we get what? Negative 1/3 minus 2, that's negative 7 over 3 for negative 1. 0 is just 0. 3 cubed is 27, divided by 3 is 9, minus, what is that, 18, so that's negative 9. Okay, so now once you've found the y values, you should be able to tell me the global extrema. So the global, or the absolute maximum value is 0, okay, and the absolute minimum value is negative 9. Alright, that's it. Okay, number 8. Find the absolute max and min values. So once again, we should be finding the first derivative and where it's equal to 0. But this one is a very peculiar graph. This is a V-shaped graph. Remember this? And notice that there is no derivative where it equals to 0. So no place where f prime of x equals to 0. So no critical numbers, you might think. Wait. But there is a place where f prime of x does not exist. Where is that? That's at x equals to 2. So your critical number here is 2. And why do we have it does not exist? Because it's a sharp turn. So therefore we need to test out the value of 2. And once again we should double check the endpoints of our interval. So 0 and 5. And let's go ahead and calculate 0 minus 2, 2 minus 2, 5 minus 2. And lo and behold, what are our values? The absolute max is 3, and the absolute min is 0. Okay? Alright. You do number 9. Same idea, okay? Find the derivative. Ooh, fractions. 2/3 minus 1, negative 1/3. Ooh, ugly, you might be thinking. No worries, we'll rewrite it this way. The cube root of x, right? And then remember, you want to set this equal to 0, so we try to solve. 2 equals 2 over the cube root of x. Interesting enough, we can rewrite this as 2 times the cube root of x equals to 2, or the cube root of x, when I divide both sides by 2, is 1, so therefore x just equals to 1. Nice. Now if you left it like that and you're now going to start testing, beware. Why do I need to beware? Remember, I also need to figure out where f of x does not exist, and where does it not exist? Oh ho ho, denominator. F of x is undefined, right? F prime of x is undefined when x equals to 0. So therefore we also should test 0, and then we look at the endpoints, so negative 1 and also 3. You need to test all 4. And if you didn't test all 4, do it now, okay? And I'll just tell you the answers, because you did this already. Well, I hope you did. Right. 3 times the cube root of 9. What is that? That's something pretty ugly, but that's okay. I can try to approximate this, or we can use a calculator. I think it's actually bigger than 0. The cube root of 9, that's about 8, right? Cube root of 8 is 2, so it's a little bit over 2. Yeah, this is like, I don't know, I'm thinking approximately 0.25 or something, probably 0.24. So knowing this, what is your absolute max? Yep, that's 5. And your absolute min, wow, if you didn't actually do this, you would have got this wrong, hey? So the absolute minimum is 0. Okay? So once again, derivative equals to 0, and double check where the derivative does not exist. Whew! Alright, number 10. Ooh, trig. Remember how we're supposed to know those trig derivatives? Remember how you used to remember them? So now let's apply them. G prime. Let's do that first when we're trying to find the global max. Once again, they're doing the candidate test, where the first derivative equals to 0, or where it does not exist. The derivative of 2 sine x, that's 2 cosine x. The derivative of cosine is negative sine, so negative becomes positive sine 2x. And don't forget, we have a function within a function. Hello, chain rule. Hello, an extra little bit of 2. We want to set this equal to 0, so 2 cos x plus 2 Sine 2x. Uh-oh, this is tough. A double angle. Remember your pre-calculus days? Sine 2x, did you remember this equals to? I hope you did. 2 sine x cos x, that double angle identity. Whoa, all that stuff is coming in handy now. Or you're like, oh no, I should have memorized those formulas last year. And if your teacher didn't tell you to memorize them, I'm going to tell you to memorize them now. Okay. Oh, why am I doing this? Because I'm making you do it. Yet, sometimes solving is therapeutic. Right? Solving a problem. It's always good. You're making these terms equal to 0. So where is cosine equal to 0? Well, that's when x equals to pi over 2 and also 3 pi over 2. Remember, we're looking at the interval between 0 and 2 pi. And then over here, you're saying 2 sine x equals to negative 1. Where is sine x equal to negative 1/2? And if you think about this, this is quadrants 3 and 4, and those reference angles are pi over 6. So I hope you can get this yourself, but I'm going to tell you 7 pi over 6 and also 11 pi over 6. Okay, if you don't remember doing this, go back and review how to solve trig equations. Wow. Lots of values to test now. G of pi over 2. G of 7 pi over 6, g of 3 pi over 2, g of 11 pi over 6, and then also, yes, g of 0, and also g of 2 pi. Wow. If you're in the classroom, find a friend, actually find 5 other friends, and split up the work so that you don't have to do them all. But of course, you gotta find 5 friends you trust, right? You can't find just any random 5 friends. I trust myself, because it's just me here by myself on the video. So I will quickly try and do this myself. What do we have? Yeah. Ooh. And so, double check your answers with mine, please. Do we agree? Say yes. So the absolute maximum value is 3, and the absolute minimum value, and it happens at multiple locations for x, but we're just looking at the value, so we're quoting the y value. Woo! Okay, if you want to take a break right now, you can. And then coming back, we're going to do one more topic, this mean value theorem. Okay, so I'm not going to tell you what this mean value theorem is, but I want you to try to discover it yourself. So look at examples 11 to 13, and then I want you to actually draw lines, okay? If possible, draw the secant line between the 2 points, and then draw all the lines that are all the tangent lines that are parallel to the secant line. Okay? So what do I mean by that? Well, let me draw the secant line first. Here's the secant line. Secant line, secant line, secant line. Okay, change color. Secant line in green, okay? Yeah, secant. Now let me draw the tangent lines, okay? Tangent lines have to be parallel, though, to the secant line. So I'm looking at number 11. I'm thinking parallel maybe here. So there's one tangent line. So that's parallel. How about number 12? What do you think? One here. Nice. Oh, one up here too. 2 tangents that are parallel. Okay, cool. How about 13? You might be thinking here? No, not there. Not anywhere else either, so no tangents. Okay. How about the rest? Turn the page. Once again, I'm asking for the secant line, then tangent line. So let me draw the secant lines first. Here's the goal. Secant line. Whee! wait a minute. It crosses an asymptote. That's not really a secant line. No secant line. Okay? And therefore, of course, no tangents as well. No tangents. Okay, 15. A is the actual value on the vertical asymptote. So, I don't know where it starts. I don't know. So, guess what? No secant line for number 15. Oh, boo-hoo. So, of course, no tangent as well. And for number 16, here's my lovely secant line. Great. Where's the tangent line parallel? It should be right here, but uh-oh, it's an open dot, so really no tangent as well. And you're like, okay, so what? Well, let's keep going. I'm going to ask you for the next 3 questions to do somewhat the same thing, but with one extra little extension. I want you to draw the secant line between 2 actual points when x is 2 and y is 5. Then I want us to draw the tangent lines that are parallel to that secant line. And then in part C, this is the extra one now, can you estimate a value where the point is what they call the point of tangency? So once you've drawn your tangent line, can you estimate where it touches the graph? Okay? So let me show you 17 first. And then maybe you can try 18 and 19 yourself. So, draw the secant line. We're going to use green again, right? Secant line. Cut 2 points. Draw the tangent lines parallel to that. Tangent lines parallel in red. Probably right about here. Good. So what do you notice? What is the estimate of the C value? The C is the x-coordinate where there's the point of tangency. Yeah, right there. The x-coordinate looks like it's approximately 3. Okay? So that's what I want you to do. You try 18 and 19 and then come back and double check. Secant in green. Tangent in red. Oh, 2 of them. Yeah, 2 of them. .7 perhaps. I don't know, 4.3 perhaps. Now, by the way, you may be thinking, isn't there one over here? Yeah, you're right, but I'm just looking at it in the interval, right? In the interval. So this is not in the interval. Not in the interval. So let's not worry about it. Okay, 19. Tangent line. Oh, sorry, secant line. See, I'm getting tired. I'm really tired. Tangent lines. Yes, yes, yes. No, don't put that one there. Approximately 2.5, 3.5, and 4.5. Okay, so why are we doing all this? Well, all this gives rise to what we have here called the mean value theorem. Okay? Just like the intermediate value theorem. Remember that stuff? So, there are conditions. The first condition is this. If f is continuous on the closed interval from a to b, and, there's more, and f is differentiable on the open interval from a to b, then, so, once you've met those 2 criteria, then there is a number c in the open interval from a to b, such that f prime of c, which is this tangent slope, equals to f of b minus f of a over b minus a, which is the secant slope. In other words, the instantaneous rate of change, meaning the tangent line slope, right, is equal to the average rate of change, the secant slope. So, informally, what they're saying is, given the right conditions, and what are the right conditions again? The right conditions of continuity and differentiability, the things I highlighted in yellow. Then it says there will always be at least one tangent line that is parallel to the secant line connecting the endpoints. Or sometimes they say the instantaneous rate of change, or the slope of the tangent line, must equal the average rate of change, or the slope of the secant line, at least once. And that's a blurb that I find hard to memorize, so I go IROC, the instantaneous rate of change, equals to AROC, the average rate of change. And that's what the mean value theorem is talking about. So finally, example number 20 today then. Given you have this function, find all the values of c which satisfy the mean value theorem on the interval from between 3 and 6. Now before we can satisfy the mean value theorem, we should double check. Is it continuous on the interval? Yes. So, yes, f of x is continuous on the interval. Now if I change the interval, let's say I made it -3, -6, can we use the mean value theorem? The answer is no, because why? At x equals 0, it is undefined, and therefore not allowed here, because it's not continuous. But because the interval is between 3 and 6, it is continuous. Okay, so knowing that, how do we satisfy the mean value theorem? IROC equals to AROC. So let's do AROC first. How do we find AROC? Average rate of change. That's f of 6 minus f of 3 all over 6 minus 3. We're going to calculate this. F of 6, what would that be? 3 minus 6 over 6. 6 over 6 is 1. 3 minus 1 is 2. 3. 6 over 3 is 2. 3 minus 2 is 1. So 2 minus 1 in the numerator. 6 minus 3 is 3 in the denominator. This must equal to 1/3. Okay, that's AROC. What's IROC? Instantaneous rate of change. That's the derivative. So the slope of the tangent line. Remember, this is the same thing as 3 minus 6x to the -1. So the derivative of 3 is 0. The derivative of -6x to the -1. -6 is a constant. Let's ignore it. We'll bring down 1, reduce the exponent by 1, and I have here positive 6 over x squared. And what am I saying now? The mean value theorem says that AROC equals to IROC. So by the mean value theorem, we know that IROC, that's 6 over x squared, equals to AROC, which is 1/3. We will have to solve for x. I will cross multiply and get x squared equals to 18. I can solve for x, which equals to plus or minus root 18. And then if I left your answer like this, you'd be wrong. Because what is the actual particular value of c? C must be equal to only positive root 18, as that is the only value in the interval from 3 to 6. Alright, and that's how you can apply the mean value theorem. Okay, a lot of stuff here, I know. I talked a lot today, but heavy duty stuff. Time for you to practice. Go.